So Seve, the chart I have in front of me, this is an interesting one. You know about binomial probability, I'm sure.
That's right. I wouldn't know how to summarize it.
Okay, let's give it a crack. Okay, so binomial probability is the study in statistics of chances of things that have a series of yes or no dice rolls or coin flips or whatever in a row and how they accumulate together.
Yes.
And so I find this is one of the most useful things and useful plots I've understood in my engineering career, particularly when debugging really brittle or like terrible systems.
Oh, huh.
Yeah. So the chart I've actually got here, this is actually one of the things I love to use. Well, in this case, it was ChatGPT for, but AI for is just generating these types of plots where you know what you're doing, but doing the maths yourself is a pain in the ass.
Takes a lot of time, yeah.
Takes a lot, and just like little things like, oh, I want the plot to be pretty, make it all the series different colors. Does a good job, you know? So what we're saying here is for n number of trials. So imagine you're flipping a coin, in this case, maybe 2, 4, 6, 8, or 800 or 1,000 times. What is the probability of getting heads on each, or what is the probability required of getting heads on each flip in order to have a 95% chance of getting that on all successes? And so there's a few caveats on there.
So I'm remembering a very useful place for this kind of chart, figuring out your test suite stability. I don't know if that's why you came up with it, but we were trying to figure out how many retries to put on our test suite, because we had random test failures, like 0.1% of the time. Some just like random things like memory issues or something. And so we're like, okay, well, we don't want to retry forever.
Yeah.
There's some acceptable thing. And there's some amount of failure that indicates it's actually a flaky test and stuff like that. So you can use this kind of distribution to figure out, okay, we want the test suite to pass 99% of the time. We don't want people to hit rerun. So what do we need each test to be at with this number of retries?
Yep.
Is that,
That's a perfect way to look at it. Yeah. 100%. The things that you learn about that though, so like in your case, is like how many tests have you got in your suite?
Right now, our core test suite has 150 tests.
150 tests. Okay. So actually like somewhere on the fairly left-hand side of this chart.
Yeah.
And so if you're looking at this, we're looking at basically a series of dropping curves. They start all the way at 1 on the left-hand side. If you're not rolling this dice anytime, then you know, probability that they're all successes is always 1.
Right.
But if you roll that dice 150 times that something might go wrong, like, I don't know, there's some statefulness, there's a array going through your server.
Right. Even
almost
if it's
definitely
a freak thing, it happens 1% of the time.
Yeah. Very well, 1% is actually terrible odds. But, oh my God.
Ouch. Okay. All right.
Yeah. I mean, 1%. So look at this. So if you have a test suite with 150 trials, you're sitting somewhere over here, right? And 1% is this orange, this sort of reddish color in the center here. It's 99% reliability. Well, your whole test suite is only going to pass something like 0.25, 0.3% of the time.
Yeah.
Sorry, not percent, 0.2 out of 1. So 25-ish% of the time.
So if my tests fail, if a single test fails 1% of the time, I have 150 tests, my test suite is going to pass 25% of it.
Yeah, if any one of the tests, if all of your tests are 9% reliable is another way of putting it.
Yeah.
Any of the tests have a 1% chance of failing at any time. Yep. The chance that they all go together and all work is actually pretty freaking terrible.
Yeah.
Right?
Yeah.
And so there's some like interesting stuff to be taken out of this. And one is actually about the complexity of systems they've outlined there. Now, tests are a bad example of this because you don't want to say, I want at least half my tests to pass at a time and you type them in separate chunks. That's super silly, right? But this is where removing false dependencies from one another and saying that I'm going to call something successful, or I'm going to retry, but instead of rerunning my whole test suite, in your case, I'm going to rerun the one test that failed.
Right.
Huge difference, right? Because you're going from 150 things having to go right. There's a 25% chance that all of them go right because there's a 1% chance that one of them goes wrong. But over 100 things, that's actually probably going to manifest.
Yeah.
Instead of going back and rolling those 25% dice twice, which is pretty bad odds that at least one of them succeeds still. You might be up to something around 50% compounding.
Right.
Pretty terrible odds.
Yeah.
If you rerun just that one test, you've compounded a 25% and a 99%, right?
Right.
Now your odds are pretty
You're
good.
good now. So if you're sitting in GitHub and you're rerunning your test workflows, that is kind of a dumb way to do it.
Yep.
If you add per test retry, you're going to be way better off.
Vastly better off. Vastly better off.
I actually had this as an idea for a startup I wanted.
Oh, okay.
And it was probably like my third idea.
Okay.
tscircuit being the first.
Okay.
And the concept was currently we don't like load balance tests, even though developers waste a lot of time on it. And by load balance, I mean, we don't have like retry systems or even run tests in parallel. Like you might have a test that you know is flaky, but you just care that it passes once.
Yeah.
And a lot of engineers are categorically against this. They say your tests should be deterministic, but I've just found that that isn't the case.
Yeah.
So
I wish they were, and I made actually a SpongeBob meme, SpongeBob mocking about this the other day. The test should be deterministic and fast. I was like, that's nice. Okay, so what about on your hill setup? In the real world, all of a sudden, the circumstances vary beyond your control. So yes, I agree in the ideal world, but there are sometimes it can't happen.
Yep.
So please, sorry, I didn't mean to interrupt. Continue.
No, that's, I mean, it's funny because Hill. Okay, so Hill is the hardware integration.
Hardware in the loop.
Hardware in the loop. That's the hardware in the loop testing. And yes, there's going to be like tons of circumstances that mess that up. I think like what I was thinking of is, for web applications specifically, web APIs, you can kind of like deploy your test suite and have each test inside of like a Lambda. You can have your test run in the cloud.
Okay.
And then you can run all of your tests in parallel and retry them intelligently. And this sounds like an absolutely bonkers idea. It sounds ridiculous. But at my last company, we had so many tests. And the CI just got worse and worse, 30 minutes, 40 minutes.
Yeah.
We would spend so much effort getting that test time down. And I was like, there's already a technology for this.
Yep.
Web servers can handle so much load and spin up, spin down. Why not just use that to run tests and then get your test suite to always go basically as fast as your slowest test, you know? So yeah,
that's definitely that's one really interesting way to do it. We have actually some good friends from our batch in YC, Blacksmith. Shout out to blacksmith.sh. They are doing their thing is they do CI specific server infrastructure on extremely high clock gaming CPUs.
Oh, really?
Because most server CPUs, right, they're workhorses, they're made for reliability, power costs, all that type of thing. For CI specifically, because there's a person, you, the developer, sitting on the other side of it, waiting for those results, you want that thing to absolutely rip, right?
Yeah.
And so we switched from GitHub to them for our test jobs. And you can crank the CPUs all the way up to, I think, either 32 or 64 CPUs. So you're fucking ripping.
Yeah.
And, you got 5 gigahertz clocks on them and, all of that magnificent type of stuff.
That's amazing.
And so we actually, for our test suite, run PyTest with XDist. So it'll spool up a process per test and do the exact same thing.
Yeah.
And then distribute it, again, 64 ways, which really does a number on the test time. Oh my, that is some
amazing.
good stuff.
Fast test time is such a huge boon to developer productivity. Like the difference between having a test suite that runs in 2 minutes and 5 minutes is somebody stopping to go get a coffee or going on YouTube, which is going to turn into 10 minutes, 20 minutes.
It's absolutely, it's a human psychology problem, because as soon as you knock yourself out of your own flow state because your tools suck, you go get distracted and you do something else. And you as you say, a coffee, or you think, and as soon as your brain has wandered, you're cooked. You want to stay in that flow state, and that means staying on the same task.
And not good cooked. Cooked can mean two things, because we can say these guys really cooked.
These guys, they did the cooking.
They did the cooking.
Yeah. These guys cooked.
Yeah, no, it's huge. This is also why I have historically advocated against monorepos, because I like the tests being broken up such that the whole test suite doesn't run each time. And it just like...
It gets harder with monorepos.
It gets hard with monorepos to make sure. And then people do these hacks. They're like, oh, we only changed this part, so we won't run some of the tests. And it's it's a path to hell.
Yeah, it's a hard path. There's no perfect path because otherwise you have a repo that has its dependencies downstream and you test but you don't test its
Exactly.
dependencies.
So you're like, oh, I can't update this thing because this guy completely broke backwards compatibility. So there's really there's no happy place.
No.
Yeah.
No, not with the mono repo. But actually, in terms of the mono block or monolith, that's the other way I look at these binomial probability charts. And I think this is really cool. And so when you have something that requires, say you have anything that requires a sequence of events all to work. Testing is one example, but just a computer functioning, you might have 100, or a circuit function, you might have 100 components in a chain and each one of them needs to work.
Absolutely.
In order for your circuit board to work, right? And if you do, you need, to look at this type of reliability chart or this probability plot to work out how often those types of things are going to fail.
Yeah.
And in the terms of design, this is where it gets really interesting for us, I think, because we're both building deterministic compilers.
Right.
And one of the questions I often have is, okay, so like, why don't I just use AI to design the circuit board for me? And again, you can come back to this and say, well, if I have, in this case, the 1,000 components in a row that need to work, and AI just, it's basically just guessing.
Right.
It guesses and selects them non-deterministically. And I end up with, I have a 99% reliability of it choosing the right one off a set of requirements.
Right.
Right. Well, my circuit is almost definitely never going to work. Even when you put it in agent mode and it guesses again, in today's tools, it's likely to change more than one element with respect to one another because it has to one-shot things. And that's where the code comes into it. You need a deterministic middleman, a deterministic compiler, so that you can make discrete individual changes rather than one-shotting everything.
Yes.
For some reason, you can't one-shot an app with an
right.
LLM today.
And that's probably, I don't think you'll be able to one-shot an app. A human can't one-shot an app. So we've achieved AGI if we've one-shot it. That's my metric.
If anything, you're just doing requirements like validation,
right?
And narrowing basically when you're talking back and forth with an agent.
Yeah,
it's cool stuff.
I really think people need to not think that AI, because historically people have said, "Oh, AI will solve everything," and that wasn't true then, for sure. It hasn't been proven true yet. We need to think like it can solve what humans do today before we think, okay, it's going to solve it all and we won't understand what's in between. Yeah. I got a comment on a YouTube video the other day, and they were like, TypeScript will be irrelevant in the age of AI because the AI will have context on all the types. And I'm like, having a deterministic middleman that kind of, can help the agents and stuff like that, very important. It's very useful to humans. It'll be very useful to AI. We're not out of the woods.
No, by far. And look, even if you are super intelligent, is a good use of that intelligence to spend it on things that are easily done deterministically.
Right.
Obviously not.
Right.
Just because I can do maths by hand, for example, on a sheet of paper, of course I use a calculator. It's vastly faster. Why wouldn't I?
Right. Absolutely.
And hopefully compilers, hopefully they look like a calculator to AI and AGI.
Yeah.
That would be incredible. Super intelligence, I really guess I should say.
Yeah. Back on binomial distribution, this is something that really every engineer in CS should know about. It really is
out of CS
like
as well.
The out of CS too. It reminds me of there's a book called I think Algorithms for Everyday Life.
Algorithms to Live By.
Algorithms to Live By.
I love that book.
Yeah. This is like I don't know if it's in there, but
this one's not. But yeah.
It's just such a useful concept because in life we run experiments. We run tons of experiments.
Absolutely.
And understanding what just the odds of failure are super important.
Yeah. And also how to break down a problem so that you're more likely to succeed.
Yeah.
Like, for example, in this case, actually, one of the times I sketched this chart in my engineering career was at Tesla when we were doing the test suite for the MegaPacks. And we had a whole bunch of test values from, again, in these real world circumstances. Some of these early packs were quite brittle. And so we were dealing with somewhat brittle hardware that we were testing on to validate the test suite, and the test suite itself needed development, right?
Yeah.
So how do you break it down? And it was literally this retry strategy that we described. People have been advocating in this meeting that we should rerun the whole test suite. And I said, we can, but actually here is the plot of this test. If we rerun the test suite, we'll have to rerun it on average 4 times.
Yeah.
And that's going to take literally hours, right, at the end of the line in the factory. Instead, if you rerun the individual test, you'll only have to run it once.
That's probably the biggest takeaway here, because so many developers sit on workflows, rerun.
Yep.
If you look at anything that tests flaky things, it has per trust retry. Like Playwright browser automation testing, that has retries built in. There's a reason for that.
Yep.
But a lot of unit test frameworks don't. They expect everything to be hyper deterministic.
And hyper fast.
Hyper fast too. Yeah. But that's not how everybody develops software. For example, we don't have many unit tests. We almost never write unit tests. All of our tests are integration tests. And the policy is kind of, if a user would write this code, that's great for a test. And how it gets done, the black box inside, not so important for a test suite. It's more like an acceptance test suite for user behavior than like specific unit tests. Of course, unit tests can be very useful for developing. So if it's helping you develop, write it. But otherwise, like for me reviewing a PR, I want to see what you're enabling the user to do.
Yep. Yeah, that makes sense.
It's a little easier to read.
No, it's a good way of looking at it too. I like these binomial probability distribution charts exactly for that reason. It shows you how to break or where to break down a problem such that you can actually tackle it in a way that you're likely to succeed. Or where to break down a flaky problem is the perfect like little caveat to put on it. So you're likely to have the thing overall succeed.
Yeah. Something we're really going off on test suites, but I deal with testing all day, so I love it. But
every good software engineer should.
Yes. If you're not testing your code, I know there's some anti-testers out there. Get real, you anti-testers. Anyway, so something else I'm a huge advocate for is I don't know if you do a lot of tests with services and networking, but I do not like third-party API calls in my test suite.
Third party, oh God, no. Yeah,
always dangerous. Even if they have a test mode. Stripe has a test mode. No, stay away. For your test suite, it's gonna slow it down. It's not gonna have that 99.9 that you need. Or 90, actually you need many nines.
Honestly, Stripe might be better than our internal API sometimes. So, I won't knock them, but
Yeah. But so what we do for every single third-party API, we create a fake black box version of it.
Oh, really?
Yes.
Wow, that's extensive. Yeah.
We always go all the way, and I always have to fight everybody on it, but all the engineers, because they're like, why are we creating an entire fake version of Stripe? Stripe has so many features. There's a lot of stuff to build. You don't have to build out every feature, but I do like to build something that basically functions like the Stripe API. And there's so much power in that because you can spin these up as much as you need. You can simulate all these different conditions with it. And there is already a spec for that fake server. The Stripe API is your spec. So it's very easy to delegate and modularize and stuff like that.
I guess as well, it's fairly straightforward to have now AI build for you because there is a strict spec.
Exactly.
You say implement something that mocks this.
AI can write them so quick now. Yeah, before AI, it was painful because
AI and Fast API. Fast API slaps. Is that what you typically use as well? Or?
No, we use. I think Fast API might be in TypeScript, but we do everything in TypeScript now.
Okay.
I actually.
it's in Python. Yeah.
Yeah. But I think it would be very fast, or it is very easy for AI to write. And I forgot where I was going with this, but yeah. They're they are a lot of upfront cost, right?
Yes. Yeah, huge.
And you need team commitment. But after you have that, and especially after you have the capital, it's just really, really pleasant. It's really easy to debug. And then what I'd like to see in the open source world is more people sharing fake versions of services that are usable.
So there's the GitHub Actions one that I've played with once or twice. I'm trying to remember. I think it's just called Act.
Yeah,
you run locally.
Yeah.
That, thank God it exists, but also, God, is that GitHub's Actions API one of the hardest things to debug and like work with in general that I've ever had?
I agree with that. I actually, that feels like an unsolved problem.
Like testing your workflows? Oh my God. Do I just have to keep pushing to a branch with like half of my file disabled and then eventually back to main when I re-enable when the trigger is?
That is basically what I do today. Yeah. I don't think I've solved that one.
Oh no, I don't know if anyone has.
Yeah.
But hopefully the fake Act actually, sort of carries through and is maintained, because it's a hard thing to do. It's something that shifts and new features that get added, and
you have to spin up containers too. It's like got to orchestrate.
Yeah.
That's pretty complex. That's not lightweight.
That is not a lightweight API by any means.
Yeah, but it's a good idea. Yeah, Fake Act, huh? Shout out to Fake Act.
Yeah, I think it's just called Act.
It's just called Act.
Shout out to Act, indeed.
Yeah, very cool. All right, let's see what we got on our agenda here. All right, so this was kind of interesting. I got to be really careful. Twitter kicks me off after 15 seconds, so I got to...
Okay.
All right. Someone got these small versions of Llama to run on Windows 98.
I did hear that, yes.
So it's kind of interesting because we've had the processing ability to do this, maybe not to create the weights, but to talk to LLMs for so long, and the fact that it's running on 128 megabytes of RAM, I'm just like, oh,
that's
man,
insane.
The implications.
Meg. I mean, you can put 128 meg on an ESP32, for example, without
yeah,
yeah.
It's crazy. So what kind of stuff can we do now on the edge?
No, sorry, that's too much for an ESP32, but you can put it on some STM32.
Can you? And this is, you wouldn't be able to like pull from Flash or something for an LLM. You would need it in closer to the CPU. Is that right?
I mean, at 128 meg, they must be pulling from storage, because there's no way you're fitting like Llama on a 128 meg. It's got more than 128 million parameters, doesn't it? Even the smallest.
I think there's a 1.3. Oh wait. You're right. What the hell are they running here?
It was probably just running really slowly,
Maybe, 128 megabytes. That means you have a lot of bits, right? These 1.2 billion, does this math? The 1.2 billion parameter models, if it's all binary.
But they're not binary models. I don't know. Well, I mean, I think people have been experimenting with binary models, but I don't think that any of the current production ones are. I think they're all either 8 or 16-bit models.
Hold on. 260K model. So they ran a 260K model at 35 or 36 tokens a second and 1 billion. Somehow they ran a 1 billion model very, very slowly.
Yeah, real slow. Wow, that's cool. Okay, and that's at, what's that, 0.00093 tokens per second.
Yeah.
Okay, yeah. But you see wow. But we could have been talking to the computers. Well, we could have been talking with AI in 98 is the title here.
It's also exciting everybody's time, classic question, what would you bring back? If you bring one thing, what would you go back? And people would say, oh, a USB with like stock market data or something. But I don't think I would do that. I think I would bring back a big model and then spend maybe a couple of years trying to get it to work on a Windows 98 PC.
Yeah. Wow. Because that's the thing. Like, I think it was Sam Altman that it was someone in OpenAI early on that was talking about this. Around their upcoming release, it was God, what was the absolute genius who left the 5-person company? Ilya, thank you, Ilya. So it wasn't actually the computing that limited us training AI models for the last decades. It was human time spans. We got bored. The researchers got bored. It wasn't obvious there was going to be some benefit, that type of thing.
Yeah.
We could have done it decades ago. And I think that's true for a lot of things. So it's the same going to Mars, right? There's nothing that's meant SpaceX needed to crop back up now. We proved that we could go to the moon in the 60s. So it's really just a motivation type thing. And that kind of makes you think, like, what's next? Well, fusion, like, are we sufficiently motivated?
Right.
For example,
it's a question of motivation.
It's a question of motivation. And so
I don't think people
exciting.
believed in AI. I was AI fatigued in the same way that I think people are crypto fatigued now in many ways, right? Like there were like these massive plans to decentralized finance and stuff like that, and it didn't play out so fast, and I got bored, and now I'm I think it'll happen, but probably just really, really slowly.
Yeah. I think that's fair.
So we got a little bit of AI fatigue when it was like reinforcement learning and like a robot picking up something.
You're like, oh, that's cute. But then actually the robot comes and picks you up, and then you're like, oh, wow, okay, now this thing's serious.
I think we have yet to see a robot demo that, a robot is like convincingly doing something better than a human with the same like physiology or something like that, right?
Yeah.
Like it's like moving, like for example, if it's like pumping through wire harnesses or something, I would go, okay, like I'm sold on that version of the future, but we have yet to really see it. By the way, quick pause. Is this mean on? It's on, right?
Yeah, that's good. Yep.
I keep tapping the mic button, and I'm like,
if you hit the side of it, unfortunately, it's just capacitor touch. So if it goes red, that's when you're.
And I'm a mic grabber. I got my hands all over this freaking thing.
Rub it all up. That's really cool though. What else have you got there?
Okay, so this one I am crazy excited about. I would love to do something.
Oh, the teensy. I love the teensy.
So
what a great one.
The teensy is great. Okay, but what this guy did is he made it so that he can overlay all the pins in VR. And I'm thinking,
so this is like the little pinout diagrams, the colorized pinout diagrams that give the function that each pin on the breakout board can provide.
Yeah.
But in AR.
That's
AR. Cool.
And I don't know how useful it is. Maybe if you're breadboarding this particular board, this could be a little bit useful. But imagine on a PCB where you're trying to like debug and you need those test points. I'm like, that's going to be so useful.
I mean, if I could do that plus like a Seve, for example.
Yeah.
Oh my God. That would be a lovely world to be in.
That'd be amazing. I've been thinking about how to make it as easy as possible to like debug digital logic on my boards, and I'm not really sure what the best. Like, I almost want a port that you plug into and you can read everything.
Yeah,
but
that's what we do.
Yeah. Okay. So you have this port that you plug in.
We put Seve headers, so they're just like a little like the 0.254 mil spaced, or the 0.1 inch, I guess.
100 mil?
100 millimeters, 0.254. Anyway, we
don't really have a
put
good
those
name
headers,
for it.
just a 2x4 header on there, and you can plug directly from a Seve logic analyzer, which it can also do under 10 volt analog at 100 megasamples a second. So fast enough for most analog signals, or 500 megasample a second digital. And we just put them everywhere, and then you plug into them.
So you have a bunch of different connectors, and you're like, okay, I want to debug that. I throw it onto
I want to debug the feedback signal between some motor and its current shunts or something. Yeah, you just plug the Seve into those headers, and you can plug into two at once. It's got 16 channels.
Oh, nice!
And you're good to go. It's fantastic.
That is a pretty good solution. Yeah. I just I'm thinking maybe I just got the Analog Discovery. Have you ever used this board?
Yeah, I have. Yeah. So, similar deal, slightly not quite as nice.
Yeah, it's not quite as nice. I've used both, and so Saline, the disadvantage, I guess, is it doesn't really do analog right now. Maybe I'm wrong.
It does do analog. It does actually quite well. It doesn't do super high speed. It's not a scope. It's a digital signal analyzer or a logic analyzer that also has analog capabilities.
Nice.
So it's not doing gigahertz of anything.
Okay.
Or even hundreds of megahertz. It can do tens of megahertz.
Gotcha.
Which is, vastly enough in most applications.
Yeah, that's going to be enough for a lot of stuff.
And it can't do signal generation either. So that Discovery can do like some, whatever. You can tell it to be a waveform generator.
Yeah. It can generate waveforms. It can be a little bit of a power supply.
Yeah, just a tiny one.
It has a little smattering of everything.
Yeah, exactly.
So it's very nice in educational context.
Yeah.
I think, because you can kind of avoid having a scope, and you have all these different little things. But Saline's digital analysis is just like,
second to none. That app is incredible.
It's so great.
I love those tools.
You kind of get this, I don't know what you call this view, where you have all these digital waveforms, then it kind of like overlays the bytes on top of it.
Yep.
But that view is amazing.
Magnificent.
Yeah.
The software is honestly second to none. The fact that it works so smoothly on a Mac, that is all incredible. And I believe they're coming out with some new stuff soon. So I'm excited to see and talk about that.
Very exciting. Yeah. I'll have to pick one up.
One of the things actually, Seve, that you are absolutely going to love coming out, actually, by the time this is released from Atopile, is we are putting together a Hill suite of modules specifically. And so when you, instead of putting the headers on the board, you can do either a debug run of your board, or you can build just a sort of side-by-side pogo board, a hill board that has, in that case, basically, whether it's a logic analyzer or a high-speed ADC or a thermistor emulator, or all of these little blocks on it to actually test and exercise your boards bespokely designed for that specific application.
Hell yeah.
So
I'll use
that's exciting stuff.
Yeah, I'm very into that. I've been thinking about ways to make it easier to debug, because I keep falling into this trap where I order a board.
Yep.
I'm very happy when the auto router works enough for me to order a board. I've been fighting the auto router for this is week 2 of fighting my auto router on one board.
Round 2 fight.
But I'm very what I think I need to add is like a way to just automatically throw on some like debug points. You know what I mean? Like I'm not going to think about it. It's just going to show up on the board. And then when something inevitably goes wrong, I don't have regrets for waiting 2 weeks to get a board and then it doesn't work.
Oh God, 0 ohm resistors go such a long way as well.
Right.
In debug mode, if you just between each little branch of like linkage on your net, you could be able to chop and change.
When you do a 0, that's a really good idea. So if you do a 0 ohm resistor, can your pogo pins kind of go on top of that 0 ohm resistor, or is it kind of like you got to take it off?
You can. I would recommend instead putting a pad beside it for your pogo pin to go onto.
Okay.
I mean, if you're manually probing, it's trivial. That's a great spot to probe.
Gotcha.
But if you want to build a pogo jig and get a reliable connection, you probably don't want to do that on the same pins.
This reminds me, there was we were talking about these USB ports that Dell was screwing on. How do you I was looking at the space of kind of like contactless or solderless connectors.
Okay, yeah.
So there's I learned that in addition to press fit, which is where you have a plated hole and you press something in, you also have compression surface fit or whatever. And that's what Dell ostensibly uses, where you have like basically vias on your board and you are fitting something, not a pogo pin, but like I think a pad
little
or a
pin,
ball or something into that hole. And then you have pogo pin, which can kind of just do any pad.
Presses as a spring that presses on a surface.
Right. Is there anything else? Are these what we have? And what do you think of these?
The other one is vertically conductive tape. And so they used to use this on like, and I assume they still do actually on LCD screens and the likes. But this is a really incredible material. It's basically like a little very squishy foam tape that only conducts straight vertically through it.
Really?
And so you can have multiple pins, like a stripe of pins underneath it, and a stripe of like matching pins on the glass plate on your LCD and top.
Yeah.
And you just press them together and the electricity will only go straight vertically through it. I basically think it has, I'm not actually sure, but conductive channels that are built only one direction, of course, or like, and they layer that somehow to enforce it. And what that practically means is that as long as you line up the screen with the circuit board, it doesn't matter where the tape goes.
Wow.
It will basically interface to that.
That's incredible. I've never heard about this. So I could take a stamp board, like a stamp PCB, and I could just pop it onto this tape. Good to go. Connected.
Yeah.
Incredible. I'm gonna buy some of that.
Yeah.
That sounds amazing. What's that called?
You can get it on SparkFun, I believe, but I think it's the generically like vertically conductive
tape.
Foam or tape or something like that. It's cool stuff. I've never played with it myself, but I've seen it used a few times, and you're like, wow, I'm gonna
find all the ways to break that. I love the idea of stamp boards, but I don't, and they're extremely easy to solder, of course, but it does bother me. I still have to solder. So
interesting. One other technology that I've considered trying to play with and I decided was just too expensive and big was ultrasonic welding on a tiny scale. This was specifically actually for debugging, is because I want a piece of enamel wire and basically a pen, and to just be able to, through the enameling on the wire, like quote unquote weld that onto a point on the board.
Wow.
Without the heat, without the damage, without the smoke, the burning, the blah blah blah, just well enough to get a diagnostic off that point.
Yeah.
That would be magic, I think.
Yeah. Is that like non-permanent? Like it's not supposed to be there for a while, or could you bring something like that to production? Could you actually use
they use ultrasonic welding in production all the time.
That is so interesting.
I want this device. I just want like basically a little pen that can solder these weld these enamel wire points on for me.
Yeah.
So I can just use them to plug into some diagnostic tool off the side of my board without the problem of, my wires shorting together or having to fuddle around with the soldering. I think it would be way faster.
Wow.
But it would be a new tech to develop. So,
that is so cool. Yeah. Lots of exciting things. I think like in the, I have a bunch of thoughts on here just because rapid prototyping is such an interesting, like there's a lot of people talking about on Twitter right now. It's particularly the guys at the Pick and Place. What's Lumen PNP?
Lumen PNP, yeah.
They have done a lot of work on laser etching. I don't know what to call it. Laser etching of PCBs. I think that's fantastic. I'm so excited about that. And I wonder how, like, if there's a paradigm shift here, especially because with atopile and tscircuit, you kind of have it's kind of like a precursor to really generated layouts, I think. And so if you have a little bit of flexibility in your layout because it's being done by AI, you can have different variations, etc. Is there a chance that we could kind of adapt automatically boards so that they can be quickly prototyped? And then everybody wants to know, how are we going to get sort of like next day prototypes or 2-day prototypes in the US for electronics? Everybody wants this.
I 100% think it's going to happen. There's too much pressure behind it. I've seen, the Uplo guys, we have played with some of these process steps ourselves on our evenings and weekends because we just think it's the coolest thing ever as well.
Yeah.
And you can just laser ablate copper straight off the front of a circuit board. You don't need a lot of the chemical parts. You still need to handle a bit of it.
Right.
But I do think there is a future in which we see basically a Formlabs printer, desktop type printer, high quality from a polished, that's reliable, in engineering labs that'll spit out your board in about 2 hours.
Yeah. Yeah.
And, then you do the assembly as well. And you're not hand assembling things. You're using, of course, a desktop pick and place, and the Lumen PMP from Uplo's a fantastic machine. I think there's a bit of a way to go there on the software.
Yeah.
But I think that with enough momentum behind that community that I see, the amount of it, we'll have that, and they do work.
We have to do it because we were discussing this earlier. The speed at which you can iterate is really caps how much R&D you can do. Labor cost, everything goes up.
Everything
when you can't prototype quickly, and we don't have that capability the same way they do it in China, where they can get like in a couple hours their prototype. So we need something like that, and I think there's something we're, with these new discoveries, with people kind of hacking on this, getting closer to rapid prototyping. I think something's going to happen.
The way I see it actually is that do you remember the pre-RepRap days of 3D printing?
Pre-RepRap. Oh my gosh. I remember RepRap. RepRap was like when I started paying attention.
Yeah. That's when a lot of people like us started paying attention. Yeah. But 3D printing has existed for 30 years, right? Like we've been able to 3D print. There were the plaster plus resin. They've had SLS, like this selective laser sintering, the melting lasers. All this
technology was developed. It was around.
The SLA, the resin hardening type printers. These have all existed as $200,000 machines for 3 decades, right? It's not just the 1 decade that we're familiar with. It's been 3, at least. It's actually a bit longer now because I'm starting to get old. But it's been a long time. And so, so you look at that and you say that, well, that technology's existed, and that quickly trajectory took us down to first the janky at-home RepRap. Let's make something as a community, as hackers, that we can replicate. And they were basically like hot snot guns, the glue guns, on a little gantry that could make okay benchies, right? They were fine.
They were doing that, weren't they? Yep. Like literally hot glue.
Like they practically were, right, at one point. So, and then it quickly advanced, and there was a lot to work out about flow rates and firmware, and someone has to come along and write the first firmware that works well. And it's often that firmware that kills you, and the slicer. Okay. And then fast forward a little bit, and all of a sudden you had an exposure out of, next it was basically Ultimaker that was born of the RepRap. And then you had things like Formlabs coming out that made the resin and like a high reliable benchtop resin printer accessible in a workplace.
Yeah.
And so I watched that whole evolution, but I think that we're at the RepRap, the dawn of the RepRap era in the at office in-house PCB prototyping era.
Yes.
And I think that what we're seeing with Uplo is really that first set of RepRaps. And actually another maker whose name escapes my mind, I saw doing the via plating steps of this really specifically, because that's the next part of this you need. But we're seeing people gel together, share ideas, build tools, share their designs on how you can actually do this yourselves in this kind of 2-hour time scale. And based on the RepRap days, I think that this is going to be something like a 2 or 3 year exercise to get a good machine going. But once we do, I'm confident we can get to great, because LPKF is already building the $200,000 version of this that does work incredibly. You can get 2-hour prototypes in-house at the moment. It's just a $200,000 machine.
Right.
We've proven it. We just need to make it cheap, it's a cool place to be.
It's a very cool place to be. And I wonder if the step prior, the design stage, if we have something to contribute to this process, like, can we generate PCBs that are, can we generate, like, when you get your output, can you get a version that's made for production?
You can.
And then a version that's made for
100%.
prototyping next day.
I 100% you can. And beyond that, beyond just the layout characteristics, this comes down to components as well.
Right.
You have to select components that you have to assemble, because you're not getting new components in 2 hours, right?
Yeah.
And so, no, you can't have maybe whatever, for argument's sake, say you don't have a 4K7 resistor for some ungodly reason, but you do have two 10Ks.
Right.
You can put them in parallel, and all of a sudden you know, these are the types of things you can do.
Yeah, I like to talk about how before electronics as code, sub-circuit replacement, like replacing an entire sub-circuit with another basically functionally equivalent sub-circuit, is really like just not something that you do often. At least. Nobody really does that.
Everyone avoids it. Everyone's scared of it.
Yep. So today, pin compatible replacements are common.
Yeah.
Like you even work with companies, and they'll be like, okay, we'll if this chip isn't in stock, we can use this and this, and they'll do all the sourcing and figure that all out. But what if instead of that, it was like, okay, this is our voltage regulator circuit, and that entire thing you can
it's fungible.
It's totally fungible. It just needs to regulate power and be a well-known, well-understood design that all the characteristics
well characterized.
Yes. Yeah.
Absolutely. That's the way it should be.
Yeah.
And I mean, we're hurtling towards it.
Yeah.
I'm not too worried about that. It's an exciting future.
Yeah.
And one, as you say, it's not just the exciting future. I mean, the prototyping is going to be one heck of a job already. That's so exciting that you should be able to do this in our scale. As long as your parts are fungible, you can just use the stuff you have to a large degree. That's incredible. And that leads you down a path where all of a sudden you can actually go think and stay in your flow state, and your engineers are something like, 20, 30% more efficient. Perhaps even double or triple, depending on who you're talking about. They either work or they don't. It's pretty binary.
Yeah.
It's a bright and really necessary future. And I'm glad to see that people are working so hard on it.
Yes, get it done. We want it. We all want it.
We're cheering for you. We're cheering for you.
Rooting for you, not completely on the sidelines, with some vested interest.
With some vested interest, indeed. Seve, I appreciate the time as always. Thank you so much. You have a good one.
See you.